Welcome to part one of the measurement notes, and today we're going to be talking about the metric system. In fact, part two talks about the metric system as well, but we're going to talk about the first part today. Now, the metric system was designed during the French Revolution of the 1790s, and the metric system brought order out of a conflicting and confusing traditional systems of weights and measures that were being used in Europe. If you can imagine living in Europe back in the day, and so you're looking at the 1790s or before the 1790s. What was a foot? Well, it depended on who was the ruler of your country. If the ruler of your country had a really large foot and you bought 5 feet of, say, cloth, well, then you got a good deal. But if the ruler of your country had a really small foot and you bought 5 feet, it wasn't nearly the same length. So whether it was someone's foot, whether it was someone's arm, no matter what it was based on, it wasn't standardized from country to country to country. And the metric system is what brought order out of all this chaos. Now, the International System of Units. Now you might say, Mr. Atun, didn't you just say it was the metric system? The metric system was the original name, and it's actually now called the International System of Units. I'm going to refer to it to the metric system quite a bit. It's not as common here in the United States, so if I said, hey, we're going to talk about the International System of Units, a lot of people would probably look at me as if I was a little weird. So the International System of Units is the modern metric system of measurements, and the SI was established in the 1960s. Now, some good things about measuring an SI. One, it's based on multiples of 10. You're going to find out very quickly that it's very easy to move from unit to unit, much more so than our traditional unit, the English system here in the United States. There are no fractions, so if you don't like fractions, the metric system is for you. We actually use decimals in the metric system. And the reason why we're going to take a look at it this year in science class is because all scientists use the International System of Units. Scientists, when they're communicating all over the world to other scientists, they use the metric system. So that's why we use it in science class. So if you get at home, or if you go home and your parents ask you, why are you studying the metric system? We use the English system here in the United States. Well, I'll just reconfirm to them that, hey, you know, we're in science class and scientists use the metric system. So who uses a metric system or the SI system? Well, basically in everyday life, everybody uses it, except for us. Well, not quite us. The last time I checked, the United States of America, Liberia, and Myanmar were the only 3 countries in the entire world that didn't use the metric system. So basically everybody else uses it except us. And here are those countries. You can see that Liberia is the country in Africa, and Myanmar is in Southeast Asia. So what does that mean for the United States? Well, the United States, actually, when we produce any products here, if you look at your tennis shoes, if you look at a lot of other products, they'll have the English system on it for a weight, for a length, and they'll also have the metric system. So there's actually some added cost by having 2 different ways that people measure throughout the world. And what we're going to be doing today is we're going to be using length. We're going to be talking about length. We'll be talking about mass today. Volume we're going to put off until tomorrow, and we may talk about a little density and temperature in part 2 as well. Length is the meter. The tools we use is typically a ruler. A lot of times we'll refer to the longer sticks as meter sticks instead of yardsticks. Volume is the liter or the cubic centimeter. That's the base unit, and it's measured with a graduated cylinder. Mass is going to be the gram. Triple beam balance, we used to use that a lot, but we don't use it so much anymore. We're going to use the electronic balances in here. Density does not have a tool. You actually have to calculate. I suppose if you wanted to say your calculator was your tool, because it's actually 2 of the above. You have to know the volume and you have to know the mass. So density equals mass divided by volume in order to make the calculations. And temperature can be recorded in Celsius. The official temperature of the metric system is the Kelvin, but most scientists use the Celsius, and we're going to use a thermometer. Now, what are the base units? A base unit is the standard unit of measurement that we will use to measure. And the nice thing about the metric system is there's prefixes. And once you know those prefixes, The rest of it's pretty easy. Pre means before. A prefix is a small part of a word that comes before the whole word. And metric prefixes equal a number, and I'll show you what those numbers equal in a little bit. And when we measure, we can add a prefix to change the value. So these are the common metric prefixes. We're not going to work with all these. Every once in a while you hear me talk about a gigaton. It's going to be a billion tons. You have mega, kilo we'll work with quite a bit. Hecto you'll have to know. Deca, deci, centa, milli, you'll be introduced to those. The nano, we may mention every once in a while, but you don't have to know. But the big ones is the kilo, the kilogram. Okay, and then we're used to the centigram or the centimeter or the millimeter or the milligram. So those are the three that are most common, but you will have to know some of those in between, and I'll show you why in a little bit. So there's actually a lot more. When you looked at this one, it goes from giga to nano. This actually goes a little bit higher, and it shows you more of them. You know, in computers, you guys are starting to talk about terabytes. Well, that's what tera means. And every one of these means a number. For example, the kilo means 10 to the third power, or 1,000. Deca means 10. Centa means 1/100th. So that first 0.01, the first spot after the decimal is the tenths, then you have the hundredths. Milli means 1/1000th. And it goes pretty small as well. So metric unit conversions. Metric unit conversions is simply a matter of moving a decimal in the correct direction and the correct number of places. And this is what really differs between a metric system and the English system that we use. For example, length. You know, we'll go from 1/16 of an inch to 1/8 of an inch to 1/4 of an inch to 1/2 inch to an inch to a foot to a yard to a mile, but they're all different. When we are in a metric system, we can go from the millimeter to the centimeter to the decimeter to the meter to the kilometer, all pretty quickly. So there are a few rules for writing the metric system. First of all, do not use periods. So for example, 7 seconds is just 7s. Leave a space in between the 6 and the label. Do not add any s's to the symbols. So if it's 10 kilometers, it's just still 10 km. You don't add an s to it. Do not capitalize unless it's supposed to be capitalized. So milliliters typically small l or small m, small l. It's not necessarily going to be large M, small l. And do not use p for per. For example, miles per hour, kilometers per hour. Use that slash in there, so it's basically miles/hour. Now we're going to go over this in a little bit, and I'm actually going to have a separate video where I'm going to teach you how to quickly convert from one unit to another, which is going to be important because you're going to need to know this on the test. Now when you measure length in a metric system, the base unit is the meter. 1 meter, if you want to write it out, is just 1 m. And a doorknob is typically about a meter high. Pretty close to meter high. It's not always exactly. And you can use a metric ruler or a meter stick to measure length. So the sticks that we have in this room are not yardsticks. Yardsticks would be 36 inches. These are 100 centimeters. So these are meter sticks and not yardsticks. Now surface area is a space that the surface covers. If you wanted to buy, for example, carpeting or floor tile, or you wanted to know how much paint you needed to paint your walls and ceilings, we have to use calculations. We have to use the rulers or the meter sticks or a tape measure, which could be in a metric system as well. We have to find the surface area of the floor. Now to find the area of a rectangle, all we do is multiply the length times the width. So you see here, if we looked at that box down below, right here, it's 10 centimeters long and it's 5 centimeters wide. So the length is 10, the width is 5. So 10 times 5 is 50. And now we have to look at our label. They were both measured in centimeters, but it's not simply 50 centimeters, it's 50 centimeters squared. Measuring mass. The base unit for mass is the gram. And 1 gram, if you want to write it out, is 1 g. And a paper clip is about a gram. If you picked up a penny, a U.S. penny or U.S. cent weighs exactly 2.5 grams, or at least it was when it was first produced. The nickel should weigh exactly 5 grams. And we can use a balance to measure mass. And in here we're going to use the electronic balance. We could go back to the triple beam balance. We used to use those, but now that we have electronic balances, we'll use those electronic balances to measure mass. Now, using electronic balance, when we use them here in class, well, first of all, they're very sensitive. So do not place heavy objects or press down with your hand. Do not put liquids on them, powders on them. Do not allow crystals directly on the tray because it might upset the balance. You might get some powder underneath the object that you're weighing. Do not go back. I've seen students go back there and set their books on it. These balances, they're not very large balances. If you have a can of soda, about a can of soda is about all it can handle. So don't go back there and try and sit on it and measure your own mass, or put your hand on it, or be pushing down and let up or pushed back down. Bottom line, if these balances break, you may owe us $100 or more to replace these. So you got to be very careful with them. And if we break too many of them, we have to go back to the old triple beam balances, which is going to take you probably 5, 6, maybe even 10 times longer to do. So these electronic balances are really nice for you. They're easy to use, so please use them appropriately. Now, we've talked about mass. What's the difference between mass and weight? Well, mass is a measure of the quantity of matter in an object. It's measured in grams, and it does not change. Versus weight. Weight is a measure of the force of gravity between two objects. It's measured in newtons, and it changes when gravitational force changes. So, for example, if you went to the moon, your mass does not change. However, your weight will change. So mass doesn't change, your weight will not change. We will be using the balance to measure mass. If I had a spring scale or a scale, I could measure weight. And that concludes part 1. As always, if you have any questions, just ask your science teacher. Thanks.